For the last session and to close the day on a high note, we are thrilled to welcome a representative from the automotive industry, David von Dollen, former head of AI at Volkswagen. David was responsible for overall strategy, technical architecture and design, and project management for AI research and applications development for the Volkswagen Group Regional Competency Center, serving North and South America. David holds a master's degree in computer science from Georgia Institute of Technology and is currently working towards a PhD at Leiden University, focusing on quantum computing and artificial intelligence. He has over 10 years experience developing and deploying data and machine learning products for enterprise companies across a variety of business domains. Now, David will share his experience with AI applications in the automotive space. David, you may take over.
All right. Thank you, everybody, for attending today. So I'm David von Dollen. I formerly worked at Volkswagen Group. My current company is called Grid Matrix. We're an intelligent transportation company. And I'd like to just say before I start my talk that the views that I present are entirely my own. I'm not representing my former or current employer with the points in my talk today. And I'd like to thank Wow AI for having me. The title of my talk is kind of morphed a little bit. It's called AI for Intelligent Transportation and Infrastructure. And there's going to be two parts to my talk today. I'd like to talk a little bit about the history of AI, what has brought us here to today. And then in the second part of my talk, I'd like to identify some of the challenges and opportunities that I see, especially in the intelligent transportation space with AI enablement. Okay, so to kick it off, humankind has a very long history of building out machines to do automated reasoning or to extract information about the universe and to help understand the universe better, to further our own understanding of the world. And we can see examples of this throughout history. You know, if we look at the ancient Greeks in 87 BCE, there's the Antikythera mechanism, which scientists believe, were used to calculate astronomical events, such as positions of planets. In the Middle Ages, Ismail al-Jazari published the Book of Knowledge of Ingenious Mechanical Devices. As you can see on the lower left, devices which would do things like serve wine and were automated. Through the 16 through 1900s, there are the karakuri, which were automated dolls or automatons, which could perform simple tasks such as writing or shooting an arrow. And in 1837, we have the analytical engine, Charles Babbage's Turing-complete computing device, which was first programmed by Ada Lovelace, one of the world's first female programmers. And capping it off in 1996, we have a picture here of Sojourner, the first off-world wheeled vehicle for collecting data from another planet. So all these, I think, are examples of humankind's relationship with machines and devices for collecting and analyzing information, which to a certain extent, I think AI does. AI to me is a tool to help us understand our world and to synthesize information. So building on this history, I'd like to jump forward in time and kind of talk about, how AI is related within different areas of science and the different subfields that it encompasses. I hear a lot of people talking about AI, and so to me, it helps to understand what it is and what the what the scientific effort has kind of encapsulated. I apologize if some of this information is somewhat redundant for folks. Hopefully you can bear with me while I take you on a little tour of what I believe AI to be. And without further ado, I'd like to point out some of the early, the 20th century titans of AI. We have Alan Turing, who arguably wrote the most influential paper ever in looking at decidability and computability of functions and basically birthing the field of computational complexity science. And Marvin Minsky, a pioneer in the field of symbolic AI, John McCarthy, inventor of the Lisp language. And I threw Claude Shannon in here because I feel a lot of AI kind of intersects with information theory, which he wrote as a graduate student. And so if we look at AI, we see many different subfields. So there's machine learning, perception, natural language processing, problem solving, decision making, reasoning, and robotics. If these topics sound familiar to anyone, I took this pretty much directly from Artificial Intelligence, A Modern Approach by Russell and Norvig. If you haven't read it, I definitely recommend reading it. I keep coming back to it. It's a great book. And essentially within these fields, we have different areas where people have been tackling different types of problems within the AI space. So within machine learning, we have different types of learning: supervised learning, unsupervised, or reinforcement learning. Perception, which deals with object detection, tracking, pose estimation, semantic segmentation. NLP, which deals with speech, information extraction, machine translation. Problem solving, which is search, heuristics, biologically inspired computing, constraint analysis. Some of those last topics might be kind of more overlapping with applied mathematics or optimization. As we might see, like artificial intelligence tends to intersect with a lot of different kinds of scientific fields. And so there's a lot of overlap. To continue, we also have decision making, which is knowledge representation and planning, reasoning, uncertainty quantification, probabilistic reasoning, temporal reasoning, and then the field of robotics, which deals with sensing, localization, actuation, mapping, and control, amongst other things. So a very wide field. When we talk about artificial intelligence, we're talking about many things. And so during this talk, I'd like to kind of focus in on two branches from this tree here, specifically on machine learning. And to talk a little bit about the history again, the term was invented by Arthur Samuel in 1959. And you hear the definition of machine learning as being, it gives the computers the ability to learn without explicitly being programmed. Or Tom Mitchell in his book, Machine Learning, gave us a very nice definition, which is a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. So a very concrete way of representing learning with relation to experiences, tasks, performance. And as the machine learning field developed, we also developed the field of computational learning theory. And this field gives us a very rich way of understanding and estimating things like generalization, query complexity, runtime guarantees. It's actually a very diverse theoretical field. There's a number of different theories contained within computational learning theory. Some of that is probably approximately correct learning, exact learning, algorithmic learning theory, and VC theory. And so I've kind of given this tree structure to artificial intelligence, and I I know that I might get a little bit of flack because some people think that machine learning or AI might be something different. And, so in reality, as many of these talks have discussed, we tend to apply machine learning and AI in a very data-driven way. Um, and and so we often intersect with engineering, algorithms, statistical learning. And so in the real world, we're pretty much dealing with, systems and implementing these algorithms in ways that are allow us to deal with data and are more data driven. So to continue my review of artificial intelligence, I'd like to kind of point a little bit at the problem-solving domain and search heuristics. A lot of optimization problems can be viewed as search problems, and I think oftentimes in the real world we encounter a lot of optimization problems. And so I'd like to kind of give a little bit of an overview of how some of these methods can be inspired by nature. And one thing to note, kind of in respect to computational learning theory, some folks within the community consider that unless you have a mathematical proof or guarantees around convergence or generalization for a machine learning algorithm, you don't really have an algorithm, you have a heuristic. And I like to make the case for heuristics because I feel that oftentimes in practice, we can apply some heuristic and observe some performance gain in practice. And so I tend to take a more pragmatic or applied approach in that context when applying to a real world problem. So one field of biologic-inspired computing is evolutionary algorithms. In 1859, Darwin published On the Origin of Species, and Turing actually proposed a method of genetic search that went unpublished. And then in the 60s and 70s, we had a series of publications where scientists tended to model optimization routines using evolutionary operators, such as recombination, mutation, evaluation, and selection. And by modeling these operators, they found that they were able to trade off the exploitation and exploration of the search through the objective landscape. And so when given a problem that there may not be an analytical solution for, these algorithms showed to be fairly robust towards finding solutions for real-world problems. Although there are not, as far as I know, not a ton of convergence guarantees. And in practice, these types of algorithms require a lot of evaluations with respect to an objective function here, but can be very useful in practice. And if we look at the different kinds of algorithms, we have evolution strategies, evolutionary program, genetic algorithms. The family can deal with the evolutionary algorithm family can deal with both binary valued and real valued problems, but they differ in how they use self-adaptation or recombination or selection or mutation. Another family of algorithms are called swarm intelligence algorithms. In 1989, Benny and Wang introduced the term, and within this family of algorithms, there's many different heuristics, modeled on birds flocking, animals herding, ant colonization, bacterial growth, fish schooling, to name a few. It's very extensive. And essentially what these algorithms do is leverage models of velocity and distance between the best solution found so far to search or explore the solution landscape. Now, why did I talk about these algorithms? Because I think in practice, you might, if you look around the literature, you might find that some of these evolutionary algorithms have proven useful for optimizing other machine learning models, which is very interesting to me, that we have these biologically inspired models mimicking genetic operators that are also evolving things such as neural networks, in neural architecture search or neural evolution. So very, very interesting stuff. Another biological inspired model that we've been touching on today are artificial neural networks. In this case, we have a model that is representing the structure of the human brain in the form of neurons and synapses, and the connections in interplay between activations given some input. It has been shown that neural networks are universal function approximators. So with a large, wide and deep enough neural network, you can approximate a universal set of functions. And with respect to the history of neural networks, the perceptron was invented by McCulloch and Pitts. It's essentially a linear classifier that makes predictions based on a linear prediction function combining a set of weights with a feature vector. And this was implemented by Rosenblatt at Cornell. And so here's a picture of the perceptron implemented in the 50s by Rosenblatt. After going through a series of AI winters, I believe there are two, we jump fast forward in history to around 2006, 2009, where there was a series of papers published by a group of folks. So Jan LeCun, released ImageNet in the late 80s, or ImageNet 5 was, I'll jump forward, was one of the early successes for convolutional neural networks, which had progressively deep layers and of hidden layers within a network with convolutions and pools of automatically extracted features. And essentially, I think the victory for these types of models was that, and in an early paper that Jeff Hinton and his group published, was through automated feature extraction. We think about the history of machine learning, folks were trying to manually construct features from data. And so what deep learning, the power of deep learning, I believe, gives us the ability to automatically extract features. But I think there's other, depending on the use case, and from what we've been discussing today, it may be more relevant to actually manually and have some introspection into those features. And I think there's some interesting work coming out nowadays where folks are looking at how to interpret the explainability of deep neural networks, or create more explanation-based learning, and try and move away from the black box. One area that I think is really interesting is combinations of deep learning and symbolic learning, where you might have some neurosymbolic model that's a hybridization of the two fields of AI, which I think is really interesting. So in 1988, the team at Carnegie Mellon produced this research work, which was called Alvin, which was a autonomous van, which had a hidden layer 29 units, and essentially took in 30 by 32 video input and used data from a rangefinder to essentially crawl very, very, very slowly along a lane around Carnegie Mellon. I think this kicked off, so this was one example of an early success of autonomous driving. Fast forward to 2018, We have various companies operating in this space where the car is processing massive amounts of data in real time, doing things such as planning and um, doing massive amounts of perception real time and multi-agent simulation to understand and predict what the objects around the car might be doing. So a massive amount of modeling and compute power being put into the car. I think as was discussed earlier today, we're still running into the edge cases and corner cases where the perception problem isn't fully solved yet, and the autonomous problem isn't fully solved yet. And I think it's going to take some time to get there myself personally, but I don't think we should stop trying, because I think there could be benefits that we may not know now for the technology, and I'll talk about that in a minute. So what has fueled some of this growth with artificial neural networks and deep learning? Well, the amount of compute has increased a whole bunch in the last couple of years. If we look at this graphic from NVIDIA with GPU capability, we can see they are predicting exponential growth with respect to their compute. We also look at different cloud providers as, I could consider those as being, enabling for AI technologies and the growth of AI. Being able to train massive parallel models on the cloud has brought forth, technologies such as GPT-3. This is not without the challenges that have also been outlined in earlier talks with, the environmental concerns, which I don't think are insignificant. And I also think one of the challenges that we face in AI today are around equitability and bias. I think it's very important to be mindful of what data we are feeding to the AI model, right? And to be really conscientious about how we're applying these tools, in the real world. So that's my take on AI. I know there may be some contention there. I welcome any questions or people who have opposing viewpoints. I think it's a great discussion. I'm glad to be a part of it. I'd like to talk a little bit about intelligent transportation infrastructure and some opportunities and challenges that I see there in this space. So first, I'll start talking a little bit and throw some statistics out there that I think are relevant towards motivating this problem. So if we look at cities today, we can see urban growth growing over the last 70 years or so. So we know that population centers are getting bigger; they're getting more congested. If we look in this picture here, they're getting more polluted. And so what can we do as AI practitioners to help with this problem? That's one of the questions that I'm asking today. And I'd like to try and answer and point to some research that I think is interesting that might offer some answers. So we know another statistic I'd like to throw out there is that this is a study from 2018. Around 75% of transport emissions come from road vehicles. The auto industry is working towards pushing this down. I think with electrification, this number will eventually, get pushed down. Although we have to be very mindful about how we create energy for electric vehicles and think about the carbon emissions that we might create with that. But, this statistic, I think, is a very big motivator. We can map that air pollution to deaths. There's millions of deaths all over the world that are impacted by fossil fuel use. And then if we think about safety, there's over 1 million deaths a year that are attributed to different kinds of accidents, bicyclists, motorcyclists, motor vehicles, and pedestrians. If we look at the share of accidents, we see that there's an awful lot of pedestrian accidents. So I think, up till this time, folks have been talking about how autonomous can cut back on deaths and on roadside deaths and increase safety. I'd like to make the case for other forms of technology that I think can also make an impact on safety. So I'm just going to give a quick overview and some applications that I think are really interesting, and maybe talk a little bit about some research and give you guys some food for thought. So here's a graphic that there's a news article that I put here from 2018 where Toyota introduced vehicle-to-vehicle to infrastructure communications. So cities are generating a lot of data today. We have different devices that are such as LiDAR and cameras and induction loops that are generating data around how our infrastructure is being used. We also are starting to see more of this vehicle infrastructure communication. So I think that's a huge opportunity there towards improving AI or implementing AI to allow for automated feature extraction and to allow human operators to extract more knowledge from and reduce the complexity from these systems. So in the prediction space, I think a very interesting place that's, a stream of research that's emerging are around graph neural networks for road network graphs and prediction. Google released a paper a few years ago where they showed a reduction in ETA for Google Maps using this methodology. And then, other groups have shown road traffic prediction, intelligent transportation using this technology, which I think is really interesting application of deep learning to this space. I was lucky to be a part of a group at Volkswagen where we released a study called traffic flow optimization using a quantum annealer, where we used a quantum computer to essentially distribute the load across a road network graph. I think most of the time, as it was mentioned in earlier talks, like it is a capacity planning problem. And so finding ways to distribute the load, and formulating the problem that way is kind of an interesting approach that I think I was lucky to be a part of the group that we took towards solving that problem. So one last thing I'd like to talk about. I think it's important as AI practitioners and data scientists and folks working with AI to be aware of societal risks and ethical concerns. Whenever we use data or build AI, I think we should think about, the implications and be mindful towards, privacy, equitability, safety, transparency, and security. Obviously, the environment, if we're trying to reduce the overall CO2 load, we don't want to increase the CO2 burden by training AI models. And I think reliability of these systems is also key. That's something that was talked about earlier. So definite challenges in this space, but I'm optimistic that over time humanity will overcome them. So final remarks, AI R&D over the last 10 years has fueled a boom in applications. We can use AI systems towards solving real-world problems of transportation safety, equitability, and emissions. It's important to be mindful of ethical considerations when leveraging AI towards solutions. But there's many untapped opportunities within our world and within our environment where we can leverage our AI superpowers for good. And so I'd like to conclude my talk with those remarks and open up the floor to any questions. Thank you very much for listening.
David, what a great talk. Cars and AI are two of my favorite subjects. Um, so, first question I want to ask you is one of the biggest puzzles for the industry is validating safety related decisions made by autonomous vehicles. In order for a vehicle to be street legal, it needs to demonstrate its ability to comply with certain safety standards. But in the context of autonomous vehicles, safety will be handled by an AI. And although current results are promising. For instance, responding adequately in an emergency braking situation, this can't really be demonstrated or guaranteed. Do we need to evolve our current safety demonstration standards as a result? And how can we make sure that these systems are really going to deliver when they're called upon?
Question. So I think that those safety standards and um, tests will evolve with the field. As we see with various companies operating in the space, there's, I see new. It's almost like daily where you hear about success. Uh, Company X is completed millions of miles of autonomous journeys and is now doing, you know. Trips in downtown areas with very low incidents. But then you hear, oh, well, company Y has done the same, but they've hit a bus, right? So we might get these new, safety corner cases that present themselves. I think what we should be really thinking about are like, what are the inherent risks in deploying these systems? I think that, in the case where we're dealing with human life, we need to take this very seriously and think about how we can make our AI more explainable. Like I was saying with um, the neurosymbolic AI, I think is maybe an area that will allow us to, introspect and define more constraints around different cases. But I'm not downplaying the amount of engineering and ingenuity that has gone into that field in the last 10 years. There's hundreds of very talented and intelligent folks working on that problem, and I'm confident that they'll find a solution. It just might take some time.
Rhonda asks from the audience, Rhoda, I'm sorry, what do you consider to be the biggest risk that artificial intelligence poses for the transportation sector, and how can these dangers be addressed?
Well, I think, um, like any other domain, I'm not necessarily concerned about AI systems taking over other systems or humans losing control. What I'm worried about are more humans using AI for for in ways that are not necessarily beneficial or ethically uh, good. So to me, the risks could be in maybe a bad actor is given access to um, systems which transportation engineers or transportation planners might have and might use that in nefarious ways. I think companies can be mindful about the data that they collect. So, for example, the company that I work for, Grid Matrix, we're a privacy first company, so we don't collect any personal information. I think that's key in implementing these systems for the public domain. To think about privacy, safety, security first, and really try and think through all the risks. I hope that answers the question well.
Sure. All right, we have about 30 seconds left. Why don't you go ahead and take a look at the questions on the right and pick a winner for our most thoughtful question contest so we can award a prize?
Right. Uh, Gosh, so many good ones. Um, I will Yan LeCun said that we will not be able to have a fully self-driving car. We still follow our current approaches such as supervised learning or reinforcement learning. How do you feel about this? Dr. Funk also had a keynote saying that we are too far away from these breakthroughs. Do you think that we are? I think I might have answered that question a little bit earlier. I think that it's a very hard problem. There's a lot of complexity to it. There's a lot of corner cases, and the risks are high, with respect to safety. But I think this is a great question, and I don't know how I can select it, but I would say Tet's question is a very good one.
All right. Thank you, David, for joining us. It's been a pleasure listening to your presentation. I would like to remind everybody to join us tomorrow from 9 a.m. to 6 p.m. New York time. The second day will start with a talk about the epistemic AI by Director of the Visual AI Lab and Professor of AI at Oxford Brookes University. I'm sure it will be a fascinating evening for everyone. Thank you all for joining us.